Okay, here we go again. Another exciting day in programming paradigms. Now, I think at the end of class last time we had just did a code walkthrough and of the game of NIM, the code for NIM, and I think the code walkthrough that we did had an implementation for the game state to be a two-digit integer with the tens digit being the number of items in the first pile and the ones digit being the number of items in the second pile, right? And then, now I forget, when is your homework due? Is it due tonight? And tonight you're supposed to, we also took a look at an implementation where the state of the game was a single digit, but it was of the form 2 to the n times 3 to the m. But then for tonight you have to do a three-pile NIM game where the game state is a single digit of the form 2 to the n times 3 to the m times 5 to the k. So anyway, are there any questions about that? If you guys started it, I've answered a few questions outside of class, but thought we'd take a minute now and see if there's nothing? No? Nada? Nix? All right. If there's a
number 2 to the n times 3 to the m times 5 to the k, what does that apply to? I mean, I get that n, m, and k are the stuff.
Are the number of items in each pile? Well, here's the thing. Actually, we should talk about that maybe for a second. In order for this to work, what do you know about 2, 3, and 5? Why didn't we use, here's a good question. Why didn't we use 2 to the n times 3 to the m times 4 to the k? Yeah. Yeah, actually they are prime numbers. And why couldn't we use 4 to the k? Because if we used 4 to the k, if something's divisible by 4, it's also divisible by 2. So we couldn't successively divide by 2. Do you see what I mean? Because they would be getting mixed up. So what do those integers have to be, the 2 and the 3 and the 5? What do the 2 and the 3 and the 5 have to be? Well, yeah, they could be prime. They actually don't have to be prime. But they have to be very closely related. Have you guys heard the term relatively prime? They have to be relatively prime. In other words, they can't have any common factors. It would actually be okay to use 3. It would actually be okay to use 3 and 4 and actually 3 and 4 and 5 I think would work, right? Because 3 and 4 and 5 are relatively prime. So even though 4 is not prime, that would still work because 4 does not go into either 3 or 5. So it could have been 3 here. It could have been of the form. It could have been the form of the form 3 to the n times 4 to the m times 5 to the k. It could have been this. The only thing is, because the way you extract one of these is by successively dividing by this. And as long as these are relatively prime, this would have worked also. So you ask, where did they come from? Well,
where do you find it
in the code? In the code? Yeah, this is in the code. This is going to be in your code. And, good question. Where is this going to be in the code? Where is it going to be in the code? Let's go back and look. Here, let's look at this slide right here. Alternate implementations depend only on redefining what? Make game state and size of pile. That's where it will be. So look, here is the code. Let's take a look at the code. Here's define make game state, and here's define size of pile. So look at the specification for make game state. It returns a game state with n coins in the first pile and m coins in the second pile. Well, for you, it will return a game state with N coins in the first pile and M coins in the second pile and K coins in the third pile.
Yeah.
So that will be, and how will you calculate? That's an easy one. That's just a one-liner because it'll be X, N to the, it'll have 3 parameters instead of 2, right? But now, that other thing will be in size of pile. Are you with me? That's this, your question was, look, your question was, oops. Your question was, where does this 2 to the n times 3 to the m times 5k, where is that in your code? And the answer is, that is in your code in the implementation of size of pile.
But even in size of pile there, I don't see anything that's 2 to the, or 3 to the.
Well, yeah, that's because this is a different implementation. That's because this is a different implementation. This code assumes a state, the state as being one 2-digit integer, where the tens digit is the number in the first pile and the ones digit is the number in the second pile. So that's a different, it's a different implementation. In fact, the nice thing about this is that we're not limited to just 9 items. Are you with me? You have some more questions?
The one today is not limited to 9 items?
Correct, it is not. And not only is it not limited to 9 items, actually I should change this back. Not only is it not limited to 9 items, it also is not limited to just 2 piles. There's going to be 3 piles. So it's going to be, what did we say? 2 to the n times 3 to the m times 5 to the k. And where this is going to, where this plays out in your code is in the definition of size of pile. Has anybody actually gotten this finished yet? Oh, good. We have a few people who have done it, the whole thing. Yeah, good. Any tips for the unweary? I mean, yeah.
I just want to make sure. I made another function under the utilities that finds the exponent.
Oh, sure, absolutely. Yeah, that is the question is, you want to make another function. Absolutely. I tell you, the functional paradigm, you do that all the time. You have many small functions. You need a function. And typically what happens is you're writing a function and you need another function. You just go ahead and write it assuming that's already been written and convince yourself that that's, prove to yourself that that's correct. And then later on you say, okay, now I need this function to do this. You write that function. So yeah, that's absolutely good. No problem. It's helper functions, whatever. Yeah, that's very common and good practice. Is everybody good? Are we good? Okay, now you guys, watch this. Of course, here not only will you would successively divide by 2 to get the n's, you would successively divide by 3 to get the m's, and you would successively divide by to get the, yeah. All right. So, but now watch this, you guys. What is this paradigm that we are in? It's the what paradigm? It's the functional paradigm, right? So, this is so cool. So, because this is a functional paradigm, why don't we have the thing that represents the state not be an integer at all, but instead, why don't we have it be a
variable?
No, not a variable. Why not have it be a function? Because we are in the functional paradigm is right. Are you with me? Mm-hmm. Now think about this. This is really cool to get your mind around. This is a great book. I compliment the author profusely. The procedure implementation. The game state is a function with one parameter. the pile number that returns the number of items on that pile. Now let me give you an example. Suppose that the game state is pile 1 has 3 items and pile 2 has 4 items, right? Do you see what I mean? Then the way we represent this is not with an integer, not with a 2-digit integer or an integer of the form 2 to the n times 3 to the m, not any of those, but to have it be a function. And look, do you see then that the function that's going to represent this game state is going to be, game state will be a function. That means that when we put like parentheses, game state, when we put parentheses game state, if game state is a function, then this works. Because isn't the first thing after a parentheses always a function? Are you with me? The first thing after the parentheses is always a function, right? So if game state is a function, what we're saying is that the function that represents this is a function such that game state 1 should return 3 and game state 2 should return 4. Now, is everybody with me on that? And of course, if it were a different number of piles, it would be a different function. If there were 7 in pile 1 and 13 in pile 2, then what should happen? Game state 1 should return No. I'm saying if there's a different number, if it's a different game state, if there's like 13 on the first pile and 7 on the second pile, then game state 1 should return 13 and game state 2 should return 7. So it's a different function depending on how many items are on each pile. Now let me ask you a question. Suppose I asked you to write function game state such that it was this particular one. Game state 1 should return 3 and game state 2 should return 4. Could you write that function right now? How would you write it? What would you say? Suppose I ask you, there's an example of game state. If I type parentheses game state 1, close parentheses, it should be 3, and game state 2 should be 4. How would you write that? Could you write that? Come on, write it for me verbally.
Well, it depends on how you make the game state.
No. I'm just saying, forget making. I'm saying just if you were to program up game state, what would it look like? Define what? Define game state, then what? Lambda what? Lambda n, then what? Well, I think you could use if. If what?
Oh.
If what? Equal, if parentheses equals n 1 what?
Size of pile.
No.
Return 3.
Well, you don't say return. It would be what?
3.
3, and then what?
Else. 1.
Wait. Is there an else? Wait.
It's the next. The else.
So it would be what? 4, and then close paren, right? Yeah, here. Yeah, is everybody with me on this? Here. So it would be what? I mean, if we were just to do that, what would we? It would be define. It would be define game state. And then what did you say it would be here? Parentheses. Lambda, and then what? N, and then what? What did you say? If what? Equals n 1 what? 3 4. Right? Are you with me? Now help me close these out. 2 more, right? Is that right? I think. Is everybody clear on that's how you would define that function. That's how you would define it. That's only if you know ahead of time. So game state 1 should return 3, game state 2 should return 4. So ahead of time, how would you program game state directly? It would be define game state, lambda x, I used x, lambda x, if O. Your code would work just as easily as this, but what did I put here? If odd x, but you could just as easily have done if equals n1. This is fine. 3, 4. Are you with me? Okay. But now here's the thing. This is the function that represents that game state. But what about a function that represents some other? So now the question is, how do you write make game state? But it should be fairly straightforward, because what does game state return? What does make game state return? It returns a what? A game state. In this particular example, what's it going to return? A what? But what is the game state in this implementation? It's going to return a? No. It's going to return a function. It's going to return this function. Yeah. Are you with me? Are you guys with me on this? Okay. So see, here's how we would program it up in this particular example. But here's the question. Function make game state is a factory. And it's a factory that, we've seen function factories before, right? It's functions that return functions. So this is so cool. I tell you, this book is a great book. This is really good. So function make is a factory. So tell me, how would you define, so here's the implementation. The state is a function of one parameter, the pile number, that returns the number of items in that pile. So here, can you tell me? Define make game state. Returns a game state with n coins in the first pile and m coins in the second pile. So now tell me, what is it going to return? A function. But now, what does make game state itself take? M and n. So how many parameters does make game state have? It has 2, right? So here we go. Lambda and m, right? So those are the parameters of make game state, right? But now, what's the next line? What does it return? Lambda, because it's returning this function. Are you with me? Yeah. So now the next one is this lambda. But now what is this lambda? Lambda x. So now what is x in this lambda? The pile number. Right. And what does that function look like? If equals x. Oh, sorry. Well, we could either say if equals n1. I think that, well, I did it odd, right? Yeah. So it would be if what? Odd. If odd x. What? N. Otherwise m, and that's it. That's it. Is that simple? But what it's doing is it's returning a function. But now what's the other thing that has to happen? What's the other thing we have to define? Not only make game state, but what? There was always 2 things that we have to redefine to re-implement the game. What was the second one? Size of pile. Now, you guys, this is so cool. Define size of pile. What does it return? An integer equal to the number of coins in pile number of the game state. But now, what is the game state? A function. So here, and what did size of pile take for its parameters? How many parameters did it take? Size of pile.
2.
I think it was only 1, which is the what? The pile number, and then it reads.
And the game state.
Oh, I'm sorry, you're right. It takes the game state and the pile number. Okay, so here it is. Lambda, game state, pile number. And now, yeah, because game state is a function. So those are the parameters, and now it's just game state pile number. Because what is that doing? That's executing the game state function with the pile number, and that's what gets returned. And look, you can put this code in there. Trust me. I mean, I could demo this, but it would just look like a regular game of NIM, but it works.
How do you modify the pile sizes?
Oh, that's all done for us automatically by, here, let's look at that. The question is, how do you modify the size of the pile? That's all done for us automatically this way. That was a really good question. Let's go back. That's done by remove coins from pile. Now look at this remove coins from pile. Remove coins from pile, what does it do? It's lambda, game state, num coins, pile number. What does it do? If equals pile number 1, what does it do? Make game state, yeah. And then what? Minus size of pile, game state 1, num coins, size of pile, game state 2. Otherwise, make game state, size of pile, game state 1, minus size of pile. So this remove coins from pile just calls what? Over, I mean, what does it call? Make game state and size of pile. So if those work, this does it. Is that slick? So just by changing those two definitions, those two implementation things, the whole thing works. Actually, our author has some, well, I won't. Let's go on. Does everybody understand how this works? Yeah?
Wouldn't you need to redefine game state? Again, so that it calls, because we wrote it with the specific numbers.
Oh, no, yeah. But what I'm saying is, hold on. What I'm saying is, we did write it with specific numbers, but the general one is make game state, which is the factory. So notice that this one is the general one.
Right.
Are you with me?
When it calls it in size of pile, you should call it game state.
Yeah, that's fine. It's just being passed as a parameter. The function is just being passed as a parameter.
Okay.
Where do you see?
Like when you go to the end of the slide.
Oh, like size of pile? Yeah.
The very last line.
The very last line.
It's calling the game state function.
Yes, and the game state function is returning however many is in that pile. So that's how size of pile. Yeah, it's kind of strange, isn't it? See, in the functional paradigm, functions are first-class citizens. They can get manufactured and passed around as parameters. And then look at this. What happens here is that game state gets passed as a parameter into size of pile. And the way we use it is, oh, it's a function. So we just put parentheses and we just put the function there. And it executes it and returns the correct pile number. The correct number of items in the pile for that pile number.
So does make game state get passed through for that, like the game state?
Game state gets passed. Game state is the parameter, not make game state. Make game state is never a parameter itself, but instead it returns a function. So instead of game state being an integer, game state is now a function. And it's game state that is getting passed. Okay, so what part is confusing? Tell me.
Just how, like at the bottom where it says game state pile number, I'm just confused about how that actually like does anything.
It's yeah. I know this is weird. Yeah, I understand. I understand why this is hard to understand. But look. Okay, first of all, you understand that this lambda game state pile number, this game state and this pile number are the formal parameters of size of pile.
Yeah.
Are you with me? Now, what we did in previous implementations, like if the game state was a 2-digit integer, then what we would do here is we'd have to have some code to figure out if the pile number was 1, then it's the tens digit, else it's the ones digit, and you have to do a quotient and a, are you with me? Okay, but here, all that computation doesn't need to be done because game state, the game state that got passed as a parameter here is a function. So we can execute that function by putting parentheses game state. And it is a function that returns the number of items in the pile if we give it the pile number. And in fact, because because this is what, because if odd x, it returns n, otherwise it returns m. So look, here, let's go back to this specific one. Go back to this specific one. Look at this slide. Game state 1 should return 3, game state 2 should return 4. So how would you program game state directly? You would say define game state, lambda x, if odd x, 3, 4. But now the thing of it is that instead of, we never define game state, we never give it that name, we just, well, I take that back. It does get that name in make game state. Maybe we should go back to see make game state.
Yeah, I think I'm just confused about how make game state, you say it's a function, a procedure factory.
Yes.
Make game state. So, I guess I'm just confused about how game state gets like produced as a function from make game state.
Okay.
Does that make sense?
Yes, that does make sense. So let's take a look at make game state. I think the thing to do is to compare it with what happens if the game state is a two-digit integer. If game state is a two-digit integer, then make game state would have lambda and m. But instead of having another lambda here, it would have some computation here to, it would return 10 times n plus m. Are you with me? And it would return that integer. Okay? So that would be, you know, it would be, instead of this being, if the numbers, like what were the numbers that we had up here, 3 and 4, it would return, so here it would return 10 times 3 plus 4. And so 34 would get returned. But now what happens is, this isn't returning 34. It's returning lambda x, if odd x, 3, otherwise 4. It's actually returning that function. So then when you execute that function, down here in size of pile, that function returns, if you execute that function with that pile number, it returns that. Yeah, question, do you have it, can you have it more specific, or, yeah?
Yeah, in here, if we have the function define size of pile, if we replace game state in both places it appears with x, everything stays the same.
Wait, are you talking about here and here?
And there, they're both replaced with x.
Absolutely, because these can be called whatever you want, and this is the formal parameter, and as long as you use the formal parameter the same way down here, this could just as easily be lambda x pile number, parentheses x pile number. That would work.
Okay. Which function are we putting in here for game state?
It'll be make game state. I think that's what I was having trouble with, is like figuring out what the actual parameter would be. Because they all like.
Well, but you see, make game state takes those two integers as its parameters.
Yeah, because like when you first start out, you do play with terms, and the first parameter
Is make game state.
which then is passed in as game state.
Yes. Yeah. Remember, it was play. Yeah, actually, maybe we should write that down.
Figure out
Yeah. Maybe this.
where it all started.
Where it all started. Maybe that's what it is where it all starts. Yeah, maybe let's see where it all starts. So it was play with turns, and then what was it? It was parentheses what? Make. Remember how we started this? Make game state. And then what did we say here? Didn't we use like 3 and 8?
3 and 4.
3 and 4? And then there was another one, wasn't there? Oh, human.
And so the formal parameter.
And so the formal parameter was 3 and 4. Maybe that's why.
The formal parameter for that make game state call is just game state, right?
For play
No. What gets returned is game
Yeah,
state.
and the formal parameter for play with terms, rather, the first formal parameter is make game state.
Oh, sorry.
Is that
Wait. Oh, is game state.
Yeah.
Yes. I see. The formal parameter. Yeah. The formal. Oh, yeah. That's a good point. So if you look at the code for play with turns, this one is game state. That's what you're saying, right?
yeah?
Yes, that's a good observation. That might clarify.
So now gamestate refers to that if odd x always.
Yeah, so what happens is game state is that function. So in this case, in this example, when we did make game state 3, 4, game state is lambda nm lambda x if odd x 3, 4. Because it gets called with actual parameters 3 and 4. Now, did that maybe, seeing where this starts, does that help?
Yeah.
Still?
Well, I'm just kind of staring at play with turns.
Yeah, maybe you go all the way back to play with turns and then do a code walkthrough from there. Maybe that will help clear it up. But yeah, this is tricky. This is tricky. Because this last code here, I mean, it's just you are executing the function that got passed as a parameter, and here this is a parameter factory, procedure factory that's returning this function. Yeah.
So N and M are kind of stored in the function.
Well, look, nothing is ever stored in a function. We have no in the pure functional programming. All functions ever do is return a value. And so the storage all takes place by what's in the parameters and what gets returned.
But because gamestate's always a parameter, it's not stored.
Yeah, it is passed along. It's always passed along. Because the whole thing is executing our functions that call each other and parameters are getting passed. Yeah. Really, really good book. Really good example. Are we good? Does everybody see how that works? This is always a little, it takes a little thinking, but anyway, I think it's very nice. Okay, now, so let's move on. We're going to go to the next chapter now. I don't have the slides posted for chapter 7 yet. But I'll have them shortly. I will have them up shortly. Now, so is everybody, so there's no more questions about the homework for tonight? Okay, now, this is another great thing about this book is that what is schema dialect of? Lisp. And what does Lisp stand for? List processing, yeah, Lisp processing, or Lisp programming. And what's interesting is that we have been using lists ever since the very beginning, but we haven't really talked about the fundamental data structure of a list in Scheme until now, until chapter 7. Because there's so much you can do with the functional paradigm without actually studying the structure of lists. We've just been using them because all functions are lists. Are you with me? So now, here's what we're going to do.
Why are functions lists?
They are, because a list, well, let me define what a list is and then you'll see. Okay, so here we go, list. Here is the definition of a list. Are you ready for this? Guess what kind of a definition it is?
Recursive.
Absolutely, it's a recursive definition. So what is the base case? What is a list? What's the smallest list you can have?
Empty.
Say it again?
Empty.
The empty list is a list. That's the base case. And what's the inductive case? If it's not empty, it's what? It's not empty, right? So look, the empty list is a list, okay? And a non-empty list, which we're going to call LST, all right, has two parts. Now, there is a really funny name for these two parts. CAR, C-A-R, CAR list is the first element of the list, and CDR list is the rest of the list. Now, CAR is pronounced CAR, and CDR is just colloquially always pronounced COULDER. And these are really weird names, and if you actually want to know the history of it, the very first, do you remember who invented Lisp?
Turing?
Oh, close, but no cigar. McCarthy. Yeah. But, and the very first implementation of Lisp was on a machine, and I don't think anybody in here has had the computer organization class before, but we have, there's an address register in the hardware of the machine, very low level. In the hardware of the machine there's an address register and there's a data register. And if you take the computer organization class, you will actually see how those registers, where they are in the CPU, in a typical CPU. And CAR is an acronym for the contents of the address register, and CDR is an acronym for the contents of the data register. And so the CAR and the COULDER are very low level acronyms for very low level hardware that just happened to be the way Lisp was developed on the very first machine, you know, so that's just historical. You don't have to know any of that. It's just, anyway, there is an obscure reason why they're called CAR and COULDER. As a matter of fact, I'm kind of surprised because Common Lisp, they ditched those names. They said, okay, it's about time we got rid of CAR and COULDER. And guess what they called the CAR function in the common scheme dialect of Lisp? First. And what did they call COULDER? Rest. And so they actually called them first and rest. But you guys who have had data structures, right? Does first and rest sounds familiar, yeah? That's what we called them when we did lists in data structures. We call them first and rest. Yeah, and they are yeah. And the book actually, our author, I'm not going to do this, but our author actually shows you some low-level linked lists of how the first and the rest are set up. Okay, so the empty list is a list. A non-empty list has two parts, CAR list and COULDER list. And here's an important thing that you have to keep in mind. CAR is an element. COULDER is a list. Okay? CAR is an element. COULDER is a list. Now, what we're going to do now is we're going to remember this, and we're just going to do a whole bunch of demos. All right? And I'm going to show you, we're going to demonstrate CAR and COULDER and how all of this stuff works in Scheme. So let's go to a demo, into demo mode. Okay, so here we are in demo mode, and I have some code up here that I'm not going to show you right now, but we'll go through some of this code here in a minute. But we have already compiled it. But we're not going to use any of this stuff right for this first part of the demo. So now let's begin by reviewing what the quote does. Now, do you remember what would happen if I did parentheses A, B, C, D? What would happen if I did this? Do you know what would happen here? Yeah, it's an error. Now, why is it an error? Because A is not a function. It expects this to be a function, right? So do you remember? Let's review. How can I write down the list A, B, C, D and have it not evaluate it? In other words, not try to interpret A as a function. Do you remember how we did that? Yes, single quote, parentheses, A, B, C, D. Now, does everybody remember that? So here now is our A, B, C, D, not trying to interpret it, not evaluating it. What was the loop? What's the loop that governs this part of the Dr. Racket? What was the loop called? Read, eval, print. Quote, the quote function The quote function is a special function, and what it does is it prevents the evaluation of its argument. So if we do quote ABCD, that's ABCD. Are you with me? So it is a special function that prevents the evaluation of a list. Okay, so now watch this. So what would happen? What do you suppose will happen if I do car quote ABCD? Now, what did we say car was? It is an element, and which element is it? The first. So what do you suppose is this is going to evaluate to if I do car quote ABCD? No, you were right. What did you say? Just A. Now, does everybody see that that's what car does? Are you with me? Okay. And now, how about the opposite? How about cooter quote ABCD? Now, what do you think this is going to give us? And will it be the list BCD? Yes, it will be the list BCD. Now, is everybody with me on that? Okay? Now, how about this? How about if we do the car of the cooter of quote A, B, C, D. Now, how about if we do this? Because what will the cooter give us? The list BCD. And then what will the car of that give us? B. Now, does everybody see that that's how you extract? Does everybody, are you with me on this? Okay. And now, how about we do the cooter of quote A, B, C, D? What if we do that? Now, what will that be? CD. All right. And tell me, what do I have to write to extract the C? The car of the what? Cooter of the what? Cooter of A, B, C, D. And that's going to extract the C. And what is going to extract the D? Wait, cooter 3 times? Cooter, really? You think cooter, 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 cooter? Oh. Quote, yeah, no, we have a difference of opinion here. Now, what do you think? Yeah, does it? You want to? You say some people say this is how we get the D. But what? Huh? What will this be then? Yeah, this will be the list with just D in it. So how would you actually extract the D? The car of the cooter, the cooter of the cooter of the cooter of. In fact, now you guys, what do you suppose? How about this? How about the car of A? How about the car of A? What will that be? Then what is the cooter of A? Now, what do you suppose this is? Yeah, why not? It is the empty list. Is everybody with me on this? Okay. Now, how about this? Now, how about the car of quote A, B, paren, C, D? Now, how about this? Somebody want to predict this? The list AB. Are you with me? And what about the cooter of quote A, B, C, D? Now, how about this? Just the list CD, right? So does everybody see how, is everybody with me is everybody understanding all these? Okay.
So is that a
Elements, yeah. Yeah, in fact, if you did, how about this? Predict this for me. How about the cdr of, quote, A, B, C, D? How about this? Yeah, but is it parentheses CD, or is it parentheses CD closed? It's going to be double print. Is everybody clear on that? It is going to be double prints. Does everybody see how that works? Yeah, so all of this nesting. So it's okay, you know, the first one can be. Now, here, let me ask you this. How would I, if I had A, B, C, D, if I have this list, if we have this list, how could I extract B? What would I have to write to just get B out of that? Just B, no parens. Now, can you do this? Let's see if you can do it. Car. We need the car of what? Of the cdr of the what? Of the car of the list. So think about this. The car is going to be the list AB. The cdr will be the list B. And yeah, I think you're right. There's the B. Is everybody good? Now, if car and cdr take apart the lists, what should we have? Something that does what? That makes a list. The function that makes a list is called cons, for construct. Yeah? Now watch this. What is the car of, quote, A, let's review, A, B, C, D. Now what is the car of this? What is the car of this? Just A. And what is the cdr of this? The cdr of, quote, A, B, C, D. Now what's the cdr of this?
List.
It's the list B, C, D. So what do you suppose cons does? How many parameters do you suppose cons takes? 2. The first one being a what? An element. And the second one being a what? A list. And it does, are you with me? So what would it be cons? Quote what? Oops, just quote A with what? B, C, D. Are you with me? Now what will this be? List A, B, C, D. Now watch, you guys. What would this be? Cons, quote, parentheses, A, B, quote, parentheses, C, D. Now can you predict what this will be? I didn't see which one you were pointing to.
Parentheses, parentheses, AB, parentheses.
A list with 2 items in it, and they're each list.
I think it's going to be a list with 3 items in it
Item 1 is AB.
instead of with 2.
I mean, parentheses, A, B, and parentheses, and then
C and then D, okay? Now, are we clear on this? Does everybody see how this works?
If you put CV in like double parentheses, then it would be what Ray was describing, right?
Let's not do double parentheses. I don't want to comment on that yet.
Okay.
But yeah, let's avoid that for the time being. But does everybody see that cons is the opposite of it undoes what car and cdr. Car and cdr take them apart, cons puts them together. But the main thing is that you have to remember that car is an element, whereas cdr is a list. But it's possible for an element to be a list. You know, so you can nest them, just as you would expect. Yeah? Is everybody good?
How is a function a list?
Well, okay, check this out. How is a function a list is a good question. Check this out. Well, suppose we do odd 7. Well, here, suppose we do quote, parentheses, odd 7. Now, what's going to come out?
A list.
A list. But of course, that's not evaluated, right? Because quote prevents the evaluation of a list. But that is a list. I mean, look, here, if we do plus 3, 4, 5, what is that? 12. You know, but if we do quote plus 3, 4, 5, what is that? That's a list. In fact, watch this. Suppose we do this. Suppose we do cons, quote, plus 3, 4, 5. Now, what do you suppose this is? You know, I don't think it's an error. What is it? What does it return? No, cons doesn't return a list. What does cons return? Oh, sorry, cons. Oh, my mistake. Shoot. I'm sorry. I'm so sorry. I didn't mean cons. I meant car. I'm sorry. Yeah, no wonder it was confusing. Yeah, okay, yeah. So what will this return? 12?
Yeah,
Plus, which is the function, right? And then what is coulter? Coulter of quote plus 3, 4, 5. What's this? Yeah, a list. So you see that these functions, they're lists. It just so happens that the first element of the list is a function, but they are lists, and you can do car and coulter with them just like you could any old list. It's cool. I think it's very nice. Good deal. See you next time.